Good afternoon, everyone. Thank you for joining us today for the Introduction to Compressed Air Systems webinar. My name is Beth, and I'll be hosting today's webinar. I'll be monitoring chat and conducting some polling at the end of the webinar. Today, we'll be covering highlights from our half-day seminar, Compressed Air Systems, which is on November the 15th in Wilsonville. We hope that after today, you'll be able to understand some of the fundamentals of compressed air and apply them at your facility to help you save energy and money. I'd also like to thank our sponsors, the Energy Trust of Oregon and Northwest Energy Efficiency Alliance. We know from customer feedback that our customers appreciate that we are aligned with these organizations to help eliminate any confusion regarding energy efficiency and renewables. Before I introduce the presenter this afternoon, I'd like to show you some tools you'll be using during the webinar. To the right of your screen, you'll see the chat window, and a polling window will appear below that at the end of the webinar. If you have any questions during the webinar, you can submit them to me, the host, through chat, and the instructor will answer them at the end of the webinar. At the upper left portion of your screen, underneath the Quick Start tab, there are some tools which I'll draw a red line under. The first one on the left is the arrow tool, and there's a text tool and a highlighter tool, and the instructor will be asking you to use those at various slides and reminding you of their location. Right now, I'm going to be introducing the instructor, Eric Bessey. Eric is a licensed professional mechanical engineer and compressed air systems specialist with over 17 years of experience. He has a bachelor's and a master's degree in mechanical engineering from Oregon State University. He's performed over 100 compressed air audits and has extensive knowledge of low and medium voltage reciprocating rotary screw and centrifugal compressor types. He's responsible for the development of AirMaster, a nationally recognized software program used to model existing and improved compressed air systems. He is a certified US DOE AirMaster Plus specialist and instructor, and is a US DOE Save Energy Now expert. And so without further ado, I would like to hand the presentation over to Eric.
Thanks, Beth, and welcome everyone. Hopefully you're awake after a lunch. If you've had lunch, I'm waiting till after this to have lunch, which is beneficial to everyone. Okay, well, I guess I have to start off by saying that I'm not solely responsible for AirMaster software, which, by the way, you can Google and it's downloadable on DOE's website. It's kind of a fun tool to mess around with. I attended graduate school at Oregon State, go Beavers, and I really owe a lot to Dr. Greg Wheeler for making this project possible for me and really launching myself into this career. And you may wonder, well, why and how did you get into this career? Well, the how is the school, and the why is I thought it was a very interesting project. I've got a lot of grease under my fingernails myself, as tinkered around as a kid with just about everything growing up, and it looked really interesting. And you can kind of see this compressor in the lower right corner is kind of a greasy engine-looking sort of thing. So I just thought the whole thing was kind of interesting. I had no idea that industries used so much compressed air, and it's very prevalent across the board. Just about virtually every plant uses compressed air, so it's very interesting. Okay, so today we're going to talk about compressed air. Why should we care about compressed air? And then, you know, I think you're going to learn to care about it just because it's so expensive and it's such an inefficient way to produce energy, to do something, cylinders and various things around the plant that use compressed air. So we're going to break this down into three major topics today. Types of controls on compressors. There's different ways of controlling them. Some are efficient, some are less efficient. System pressure. How much should or do I compress my air to fill the pipes? What do the end uses need? And then lastly, leak reduction. And leak reduction is really not just about leaks. And here we're going to talk about demand a little bit. All the uses of air. A leak is really just a use of air. It's not the ideal use of air, but it is there. And out goes the air. So let's take a look. The first thing I'd like to do is ask you to use your wonderful arrow tool in the upper left corner. I'm going to click on the arrow, and I'm going to select who I am, and I'd like you to do the same. I happen to be an engineer consultant, and just like it looks like a couple of you are the same, it kind of helps me, you know, maybe craft my presentation a little bit towards you. And we have some energy managers, consultants. Do we have any plant people out there, end users or facility managers of actual plants? Looks like we have another engineer consultant. This is great because engineer consultants can get out into plants, lots of plants, and help them realize potential opportunities and point out good things that are done with compressed air. A lot of plants are really doing a lot of good things nowadays with compressed air, but there's room to go, and that's what we're here about. And November 15th, there's a lot more you can learn on the half-day course. Okay. Possible myths about compressed air. Myths. Well, let's see. Where do myths come from? Well, they come from kind of preconceived notions or really out of ignorance. Not to badmouth anybody. I certainly didn't even have any of this myths because I didn't even know anything about compressed air in the beginning. But I sort of came across a couple things, and I learned that lots of people think that compressed air is free. It's sort of just there in the pipe, and if you want to hook up an air tool to it, you just go ahead and do it, and you don't really think about the consequences of it. More pressure is better. Our system operates at 100 psig, and production needs 100 psig. I can't tell you how many times I've gone into a plant and asked them, what's your minimum plant pressure requirement? It's 100 psig. And a lot of that is driven by the fact that the compressor manufacturer rated their machine at 100, so people think that they need to operate it at 100 psig. So that's sort of an education process to find out what does your plant really need to operate and keep production going. Okay, why should we care about compressed air? This is really a fascinating slide. If I take a look at a life cycle cost of a compressed air system over 10 years, there's a lot of things that go into it. One thing is, your first purchase of the compressor itself, and that might represent 12% of the cost. If I get my little highlighter to work, there we go. 12% of the cost. That's right up front equipment. Now you look at that and you say, well, 12%, that's it's significant, but it's certainly not the largest piece of the pie. So I like to look at this, and I always challenge people, over the course of 10 years, if you can purchase some energy efficiency options for an incremental, at an incremental cost to the first cost, why not do it? I mean, it might be 12, the value might be 10 to 12%, to 14%. It might be worth it to go ahead and pay for it, because over the cost of 12 years, it's spread out, and it's not that much. We have another 12% for maintenance, just taking care of the compressors, changing the oil, filters, whatnot. But look at this over here. Over 3/4 of the pie of the life cycle of 10 years of the compressor goes to electricity. Now, I would ask you to question even this 10 years. Why am I talking about 10 years? Well, 10 years is sort of a ballpark figure of, well, a rotary screw compressor probably needs to be rebuilt in the course of that. After that, it still has plenty of useful life potentially, but maybe 10 years might be time that you consider replacing it. But I've seen rotary screw compressors go, even back in the 80s, they're still going. So my point being is that this electricity becomes even a larger piece of the pie if you consider more years. So if I operate a 100 horsepower compressor over the course of a year, 6,000 hours, that's Monday through Friday, 24-hour shift, 7 cents a kilowatt hour, which is pretty reasonable for around here. Certainly more down in California. But here about 7 cents, that's $30,000. That's just for the first year. And if you were to go and purchase a compressor, it would be a little more than $30,000, and that probably would not be for a variable speed model, but for your average constant speed, fixed speed that is, new rotary screw compressor, somewhere in the ballpark of maybe $35,000 to buy a new one. So in the first year, you've almost spent as much money as it costs to buy it. Okay. Application. This is a great one. Let's suppose that we have a weight and we want to lift the weight. So I have it up here, and I go around a pulley, and the weight is lifted. And let's say I want to apply a 1 horsepower motor to lift that weight? Well, I can do it perhaps with an electric motor, or maybe I want to do it with an air motor. So I'm going to use compressed air to operate an air motor, which would give me 1 horsepower at the shaft. Okay, so we're doing the same work. What about the cost to operate both of these applications? This is a shocker. The 1 horsepower electric motor might cost $200 a year. If I do the exact same job, same operating hours, same weight, same everything, except I do it with a compressed air motor, $1,500 bucks. That's 7.5 times more than the electric motor. And you might scratch your head and go, wow, how is that possible? Well, there's a middleman in between the electricity coming into the plant and this air motor. And that middleman's called an air compressor, that we have to compress the air. And compressing air is very, very inefficient. A lot of heat is generated that goes to do no good, and there's just a lot of losses. So that middleman really takes a bite out of our energy bill. So you can take the difference of it. Looks like about $1,300 of it could be saved, and so boy, you could operate a lot of 1 horsepower motors if you did straight electric. Okay. Polling question. All right, you know the routine. Pick your arrow. And I'd like you to think about your compressors and what kind of controls those compressors have. You may know, you may not know, and if you don't know, that is great because that gives me something to do, and we can talk about controls. And we're going to go through each one of these today, and we're going to go through them in sort of a brief fashion, more on November 15th. Excellent. See a couple options there. People were picking. All of these are, they're out there, and they have their benefits and drawbacks. So I see a variable frequency drive, start, stop, and a couple of I don't knows. Okay, modulation. Let's talk about these control types, and maybe after we're done talking, you might say, you know what, maybe I do have some of these other control types. Okay, let's go over these. Start, stop. Start, stop is really nothing more than an on-off switch. When pressure reaches a low set point, the compressor starts. When it builds pressure and hits a high pressure set point, it shuts off. It's kind of like your compressor you might have at home. You're running your nail gun, you're putting down those nice hardwood floors, and you have what they call a little pancake compressor, which is just looks like a pancake. It's got a flat tank, little compressor on top, and it just runs, shuts off, runs, shuts off. Or a gas station compressor to pump up your tire. Okay, not particularly suited for large motors because large motors, it's very hard on them to start, stop them, hard on the motor windings, there's heat, and hard on starting gear for sure, electrical gear. Okay, modulation control, or as I like to call, put a sock in it. If you were to take the air cleaner off your car and stuff a sock down it, it wouldn't be able to draw any air, and the car would probably die. Modulation compressors are very, very similar in that all we do is restrict the air inlet to progressively reduce the compressor output. There's a valve that closes, creates a pressure drop, and the compressor just doesn't have the air to bite into. Hence, it doesn't go out. So that's how we can modulate or vary the flow through the compressor. Load, unload. Load and load is kind of a variant of start-stop, except instead of stopping the compressor when we reach another point, we unload the compressor. And what it means to unload the compressor is the oil sump is allowed to blow down, so the compressor is no longer fighting against full system pressure. Incidentally, with modulation, you are fighting against full system pressure. It does not blow down. But with load unload, it does, and it's kind of like you're at a stop sign with your car. You have the transmission in neutral or the clutch in, which is hard on clutch components, but that's another subject. But you're sitting there and the car is just idling. It's using some fuel, but nothing compared to when you're driving. So you're just kind of idling along, not doing any work. You're not going anywhere. The compressor's not putting out any air. It's just waiting for that low pressure set point to be reached. variable displacement. Just as the name implies or says directly, we're going to vary the displacement of the air compressor. And you might ask, well, what does that mean? How is that accomplished? Well, if you had a four-cylinder engine in your car, four-cylinder engine in your car, and you unplugged one of the spark plugs, you would now be down to 75% displacement of that engine. And it would produce about 75% of the power. Not exactly, but you get the idea. You're varying the displacement. That one piston is no longer involved in the displacement of the engine. It's not doing anything. Okay. We see them in reciprocating compressors where we can unload cylinders. And rotary screws also have a mechanism where they can vary the displacement. More on that on November 15th. All right. Variable frequency drive. This is kind of the hero of the day, isn't it? Everybody's talking about variable frequency drive and handing them out like you know, the vaccination to the plague. Everybody needs one. Okay, what do we do here? Well, just as the name implies, even if we take the word frequency out of it and replace it with the word speed, that's exactly what we're doing. We're varying the speed of the motor. And just like your car, when you vary the speed and slow down, your car slows down. We put out less air out of the air compressor. Very well suited for trim duty. And we'll talk more about what trim duty is and what other kind of duty there is, which is called base load or off, and maybe a variable frequency is not well suited for those. Certainly if it's off, you might not need it. Why'd you buy it? So let's go on and take a look at some details in inlet modulation. Okay, so here on the left, we have air whooshing in to the if I can draw into the inlet. Okay, just as you can see in the arrows above, the air is going up through the inlet past this butterfly valve. Okay, just like an old-fashioned butterfly valve in your car in a throttle body or a carburetor. And then off it goes. Now this butterfly is fully open, so this allows the compressor to put out as much air as possible or fully loaded. Okay. Now, once the pressure in the plant begins to increase, eventually I better do something about my compressor. If it just keeps pumping along at full load, pumping up the pressure in the plant, eventually safety valves are going to start to blow and in general bad things will happen. So I want to limit the amount of air. So I close the inlet throttle or inlet butterfly valve partially to reduce the amount of flow. And you can see down below we sort of have this qualitative 2 arrows compared to the 5 on the left. So we've reduced the flow. Your compressor, if it modulates, may have a different type of valve. It may have like a piston type valve or a poppet type valve, which really does the same thing. It's a sock. It's just closing off the inlet, reducing the amount of flow that goes through. Same thing. Here's a real compressor. And the air comes in through the inlet, okay? It goes through what we call the air horn. That's where the air kind of goes through. And then down here is the actual air compressor. Okay, this is the air end of the air compressor. It's the thing that's actually producing air. It's like the engine in your car. Right here is a shaft where we have the butterfly valve. So there's a butterfly valve in here. And as this shaft rotates, that butterfly valve can move. That butterfly valve shaft is connected to an arm. The arm is connected to a linkage that can move back and forth, as shown by the arrow. That arm is then, or that linkage rather, is then connected to another arm. That arm is connected to a pin that goes into a diaphragm here. And as system pressure builds, it puts pressure on the diaphragm. The diaphragm moves the linkage, and then closes off the butterfly as needed. then once the pressure in the plant reduces because we're taking out air, let's say we increase the demand, turned on another production line, then the pressure will drop, and then the spring over here will pull the throttle open. So it normally wants to be open. If I left it alone, it would be open, but once we apply pressure to the diaphragm, it will begin to close. Okay. And, you know, this is very, very, very simple. Nothing complicated. It's kind of like the linkage on your old carburetor. And modulating compressors amongst them all, none of them operate very differently. There's some electronics that can be involved, but they all kind of do the same thing. Okay, so if I take a look at how that compressor performs, I may have implied earlier that some of those controls were not particularly efficient. And inlet modulation is a very effective but inefficient way to modulate or way to part load a machine. Way up here at 100% flow, you can see I have average percent capacity of the machine required. If I need 100% flow, then I'm going to use 100% power. That kind of makes sense, right? So there's my power on this axis over here, the y-axis, not to get too complicated. Now, once pressure builds in the plant and I need to reduce the flow, I close the inlet valve and it goes down this performance profile here, this graph. You can see my nice lovely arrow. That's great. Thanks, Eric. So we slide down, and let's say I need 50% flow. How much power do I require at 50%? You know, a whopping 82% about. I mean, that's a very high percentage power for only 50% flow. And then if, let's say I have another compressor or two operating in the plant, and they're running, and they're meeting the complete demand by themselves, and my modulating compressor doesn't need to do anything, and I slide all the way down here to zero flow. Look at that. That's 68% power. Still required. The compressor's not doing a darn thing as far as helping my plant go. It's just sort of fighting itself. It's still maintaining full sump pressure, so it's still pumped up to that 100 psi, but nothing is coming out the check valve. And I've essentially put my hand over the inlet, and it's just, you know, like I said, it's just kind of fighting itself, not really doing anything. Okay, so that's modulation. What's next? Let's look at the perfect control. Start, stop. We talked about start, stop control, on, off. And on average, just as you might expect, it's simply a one-to-one relationship of flow versus power. So at zero flow, it's off. At 50%, it's going to cycle. Start, stop, kind of like a clock. It just goes tick-tock, tick-tock. Half flow is exactly 50% power because it's on half the time and off half the time. Okay? Let's look at a variant. Remember I said there's another control type that's similar to start-stop, but instead of stopping it, we're just going to blow down the sump. And this is what I call an ideal load-unload. So we have 100% power, again, at full load. But then instead of shutting off the compressor and cycling, we blow down the compressor. And this is kind of nice because that way I'm not banging the motor, you know, stopping the motor. It still runs, but it gets to relax and not do very much. It's still turning the compressor, but instead of compressing to 100 psi's, in the case of the modulation compressor, it's only maybe compressing maybe to zero, you know, atmospheric pressure, or some compressors maintain a sump pressure. So this value, it could vary between, you know, maybe 15 to 30%, depending on the sump pressure that it maintains. Okay, now this is ideal. In the real world with load-unload, we're going to get something more like this. And this is kind of closer to reality of what you'll see. As you might imagine, the compressor loads and unloads against a system volume. So if you have an air tank, I mean, you have to have some volume. It's just like your tire. I mean, if the tire had no volume at all, like these little skinny bike tires, so you pump them up, and it doesn't take any time at all to pump them up. But if you had a really, really big tire, then it takes a while to pump it up. So the more storage you have, the longer it takes to fill up, but more importantly, the longer it takes for the system to drain down. I'm not going to give it away, but we're going to talk more about this on November 15th as to why you actually get this curve. Why does it look like this? More on that on the 15th. Okay, the next control strategy is kind of a hybrid. It's a mix of control strategies that we've talked about, where in the upper range, I'm modulating. Okay, that looks like that nice straight line. I throttle back to 80%, and this number can vary. It might be 70, it might be 50, whatever it is. But once it throttles back to that point, pressure will build to an unload set point, and then we'll blow down. So then this part of the curve kind of looks like our load-unload curve. Same power once it's fully unloaded. I mean, if it sits there all day and unload, they're both the same. It's only when we cycle the compressor that we get these other particular curves, strange-looking curves. Okay, what's next? Variable speed. Variable frequency drive is one way to achieve variable speed. There's also some hybrid motors, some DC motors, but variable frequency is the most common. And you can see that it performs very, very nicely, approaching start-stop performance down below. It actually, at 50%, kind of nails it. Variable speed compressors are really, in general, they're the most efficient at half their speed. And then as you speed them up, they lose some inefficiencies with aerodynamics and whatnot. Windage starts to take, so it starts to deviate a little bit from the start-stop, all the way up to, now what is this? What do I see at 100%? How does that 100% full load power, or 100% capacity power, compare to the other control types? Looks like it's a little higher. Well, just as in the case of the middleman being between the electricity and our air motor in the previous slides, a few slides back, there's a middleman here, and it's called the actual drive. And we have to take the electricity coming into the plant and do something with it to make it suitable for the variable speed motor to handle it. And that middleman, not to get too fancy with engineering terms, but I'll just call it a heater. I mean, that thing just sits there. If you put your hand on a variable frequency drive unit, it's hot, or it's warm, and that's energy. So that's an efficiency loss, and that's why we have that. So you might ask yourself, gee, should I buy a variable frequency drive compressor and operate it at full load? Well, no, for two reasons. One, it's less efficient. Secondly, why would you pay an extra $10,000, $20,000 for a variable frequency drive if you're just going to base load it, operate at full load? That would be kind of pointless. So I think you can see that. But anything below about 95% of full load, and you're in the money. And you can clearly see the differences in the benefits. Improving compressor controls. We've seen some controls that are very inefficient and others that are more efficient. So with your system and with every system, we must have at least one compressor that part loads. Okay. Somebody's got to pick up the slack. They're not all going to run fully out, and they're not all going to sit off, of course. So I'd like to base load some compressors and then part load with one. We've seen the inefficiencies that come in when we part load a compressor, so the least number of compressors we can part load the best. Base load them, trim with one, and then the one that is trimmed, make sure it's efficient. Inlet modulation is very inefficient and should be avoided. Although very effective, the power does not fall very much as the flow drops off. So consider load-unload or VFD control for the trim compressor. If you have a nice compressor that blows down to near atmospheric pressure, then provided you have adequate storage, big thing, more on that November 11th, then you can achieve pretty efficient part load efficiency with a load-unload compressor. But for part load, for my money, a variable frequency drive is probably about as good as you're going to get. So consider that. Okay. Example. Let's say I have a 100 horsepower compressor, and it's capable of putting out 500 CFM at full load. And let's say that throughout the day, my plant flow varies. You got lunch time, break times, full production, etc. So the flow varies, but let's say that the average is right dab in the middle at 250%. So it's going to go up and down in power, but I have an average of 72 kilowatts. Okay? Pretty inefficient. What if I were to replace that compressor with a variable speed or variable frequency drive compressor? Same flow. It's end uses and leaks that dictate flow demand, not the compressor itself. So I have the same flow, but I can get by with 41 kilowatts for a savings of 31 kilowatts, 186,000 kilowatt hours a year, and at 13,000 bucks. So I've saved $13,000 by considering a variable frequency drive compressor instead of modulation. This isn't magic. This is pure, simple application. All right. Okay, we're done with controls. Pressure's next. So let's all talk about compressor, and this is fun. You can pick your arrow. See, we interact. I'm going to be a high pressure guy today. I'm greater than 120. Okay, we see a couple people that don't know. Perfect. Love it. I love it when people don't know, because then that gives me an opportunity to help you to maybe come into your plant to see if we can't lower the pressure. I'll tell you, most people that don't know what their pressure is are typically operating higher than what they need. And just as when you were a kid pumping up that tire with the handheld air pump, it gets harder and harder to pump up your tire as pressure increases. Just as with that, compressors have to work harder. And guess what? The meter spins faster the higher pressure that you want to have in your plant, that you achieve to have in your plant. These guys are great, the 120s. These guys up here, the less than 90s, on average, these guys have already done a pretty good job at taking a look at what their plant needs and lowering their pressure. Now, can I just lower the pressure willy-nilly? Just go, I'm going to walk up the compressor and load and turn down the pressure on the compressor? Maybe not. But first, let's take a look at how much it costs to elevate my pressure, compressed air pressure. Rule of thumb. Love rules of thumb. This one's actually a pretty darn good rule of thumb, and it pans out. I've taken measurements. I've verified this rule pretty closely. For every PSI that I reduce my system pressure, I can save about a half a horsepower. Okay? 10 PSI reduction, 5% savings. That would amount to $1,500 bucks a year on our original 100 horsepower, $30,000 a year job. I could drop off 5% just by lowering it. Now, can I just walk up to the compressor and do it? Just like I said in the previous slide? Probably not, maybe not. Now maybe, but there may be some barriers that are keeping me from doing this. In the next couple slides, we're going to talk about those barriers that are preventing me from lowering my system pressure. But here's another thing that comes along with elevated air pressure. Artificial demand. Now what the heck is that? Artificial demand is defined as the increase in air demand simply because you're elevating the pressure of your system. You're operating the system higher than you need to. Imagine you walk up to somebody you really, really dislike and you decide you want to let the air out of their tires. I don't suggest you do this to yourself or your spouse, your significant other. But what does that tire do when you first push in the valve? It hisses like crazy. And then as the pressure depletes from the tire, it hisses less and less. Plants are the same way. They're kind of like a big tire. And you can save approximately 0.5% of air for every PSI reduction in air pressure. When you elevate pressure, leaks leak more, and you can shove more air inside cylinders. So it's not just the leaks, but it's the end uses as well. Also, you tend to get, unless they're regulated, air tools will spin faster. Everything uses more air when you elevate the pressure. And the exception are regulated uses, of course, because they see the same pressure all the time. So we kind of have a double whammy here. We can save power and we can save airflow, which in turn saves power. But can we just lower the pressure of our system? No, there may be barriers. And those barriers are called pressure drops in the system. And these things can be anywhere between, I got a clogged line. I mean, a 2-inch pipe that's very, 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 very old and has seen water and eventually can rust and corrode up. That'll create a pressure drop. The end uses still need what they need. And if there's a pressure drop in the system, that means I have to jack up the compressor at the source, the pressure at the source. Distribution systems could be looped. That's an improvement opportunity here. If we have a looped system instead of just a linear system, down a line, kind of like emergency fire sprinkler systems, then I can feed end uses from both ends. More on that on November 15th. Quick disconnects. Boy, these can be big sources. You get the cheapies. Not only do they leak in the end because the O-rings go bad, but they're also kind of small in diameter, and not a lot of air gets by them. I mean, it really creates a big pressure drop. Here is one that people don't necessarily, it's kind of not intuitive, they don't necessarily think about. But if I have more air flowing through the pipe due to leaks, so I have the same end uses, but I spring a leak at the end, more air has to flow through that pipe, and just like it does in the water in your house, and when you flush the toilet, the cold water drops and all of a sudden your shower gets really hot. That's because the cold water can't get there. Same thing. More leaks, higher flow, higher pressure drop due to the velocity. Velocity is just a fancy word for speed. Not getting too technical. No vectors here. Okay. Next slide. Okay, what I'd like you to do is take your highlight tool, so that's 1, 2, 3, 4, the 5th button over. Choose a color and mark on here what you might see as interesting or problematic, or otherwise you just want to know what the heck it is. All kinds of things in this room. Looks like there might be a beaver and a duck down here fighting. Looks like the beaver's winning. Go Beavs. Okay, that's another thing. That's coming in a few weeks. Okay, so yeah, mark on it. Okay, I see somebody's marked this valve up here. Somebody's marked something over here. What's that? We'll talk about that. Okay. Circling those blue things, in particular what's at the bottom of them. Okay, so what do we have here? Well, I'm going to pick a dark color so we can see what the heck I'm pointing at. These blue things right here, those are filters. And filters serve to remove contaminants from the air, either aerosols, liquids, or particulate matter, in hopes of cleaning up the air so that downstream end uses see clean air. Well, this plant said, well, we got a filter in here, and we're still getting dirty air downstream, so we're going to put more filters in. On the previous slide, we talked about pressure drops. Sources of pressure drop. One source is multiple filters, because you can't clean unless there's a pressure drop. I mean, it's almost part of the definition. You have to go through a membrane, a cyclonic effect. Something has to happen to clean the air, and one of the results is, one of the outcomes is a pressure drop. Now you look up here, they put more filters in, created a pressure drop. Eventually they had such a huge pressure drop that they had to, as someone's pointed out, they had to crack open this bypass valve. The filters are going through this line back here where someone's drawn. This, by the way, is probably a check valve, which is another device, which also creates a little bit of a pressure drop, but that's not the point. The point is that the filters are allowing air to flow through this back line, and then the bypass line is right here. It's cracked open. I'm allowing some of the air to get by so I get pressure downstream. And what I ask is, well, gee, if you're bypassing the filters, then why do you need all the filters? So you're obviously subjecting your system to dirty air. You've been getting along just fine, so what's up with that? Probably the solution here is to remove those filters, replace it with a nice, larger sized, adequate filter, even beyond adequate. But don't replace filters with filters that are too large. Filters actually can be too large, and then they don't do a good job at filtering, even though there's no pressure drop across them. So you must size them appropriately. Okay, so someone else has circled down here on this pipe. What I see on here on this pipe is a lot of goop, and I think that this airline here is in a compressor room where there's a lot of oil. I mean, this might be a sawmill where it's kind of dirty, and so of course, dust and particulate grab onto that. Not particularly harmful to anything. It's just that this kind of stuff right here can actually coat. Up here you see the fan with the cooling It's basically a radiator with cooling coils in there. Those can also clog up with particulate matter, and then they don't do a very good job cleaning. So I see some opportunities here. Replace that filter, close the valve, and do a good job at cleaning the air. Okay? Take your highlighter and mark what you see here on this picture that might be interesting. You see some compressed air lines. This is the roof of a ceiling, rather, the ceiling of the inside of a warehouse. And so they have a network of pipe that runs around on the ceiling, and when somebody needs compressed air, like they install some sort of production line or end use, then they simply tap into the network up above and drop a line down and plug it in. Well, it looks to me like someone's already identified something interesting, and that is in between this pipe and this pipe, for whatever reason, they weren't getting enough pressure over here. So they thought, oh, I know, I'll just sort of make a loop and connect it with this little 1/4-inch rubber hose. So you can kind of imagine that there's a loop here. So this line over here is being fed from the top and also from the bottom around. The trouble with this is, and there's really a couple problems here, the hose itself is very small, rubber hose, not a lot of air can get through there, and the quick disconnect fittings on the ends. These things can be small, not, poorly designed, and not allow a lot of airflow to flow through. So that's an opportunity there, I think. So pipe it in. I mean, if you're going to connect one pipe to another, put it in with the same size line at least. Let the air get from point A to point B to better serve the end uses. You might have some end use, inevitably you have some end use somewhere. I know that's the ceiling, but if you have some end use and that end use is screaming, hey, I need more pressure. Well, guess what? The operator goes back to the compressor room, jacks up the pressure. For every PSI, I'm spending 0.5% more energy, all because of an inadequate or underserved piping system, under-delivered piping system. Okay, circle it. What do you see? Highlight it. What's interesting here? Okay, a couple points there. Very, very good. Yeah, this is the whole kinds of, there's a bunch of not right going on here, and I'll show some of the things that I see, and you may see other things. And you might see this picture again on November 15th. And if you think of anything additional, you can bring it up then. But this compressed air comes down the line, and then they say, hey, I'm going to split it. I mean, this is just like Christmas, right? Plug all your lights into one socket, which does what? Well, it can burn the house down. And not that we're going to burn the house down here, but bad things can still happen. Meaning that all of these uses are pulling off this one poor little outlet, and you get a pressure drop, which is really what happens when you plug lights into a light socket. You plug too many in, you get a voltage drop, which increases the current, increases heat, burns down the house. Okay, we're getting off topic here. But suffice to say that this is poor practice in general. We see another one up here. All these little end uses. Look, we've got a foot pedal. Maybe it's controlling this, something to do with its chop saw. Maybe it lowers and raises the chop saw itself. And then what else do I see? Oh, somebody's highlighted this. Yeah, that's running on the ground, isn't it? Well, just like horses, forklifts drive on the ground, and they step on things. And when forklifts run over hoses, the hose loses. And eventually, you get fatigue and wear and holes and leaks in your hose. And leaks not only waste your precious air, but they also increase the pressure drop because of the velocity through the air. So there we go. Lots of interesting things here. Okay, next. Okay, pick it. How many leaks do you have? So, pick my arrow, and I'm feeling particularly leaky today. Why not? I've been to a plant where over half the air was going to feed leaks. Seriously. Hadn't been tended to in years. Leaks grow like weeds. And if you're like my yard in the moss, it'll get away from you very quickly. And that can happen. Sawmills, their joy and mission in life is to beat themselves to death and make the maintenance people run around and fix things. And when things beat themselves to death, leaks creep up. Okay, so we have a lot of people that don't know what their leaks. I'm telling you, if you don't know, there's probably an opportunity, which is great, which means you can take home what we learned today, attend November 15th, fix your system, save energy. Out of a plant's demand, typical. Perhaps only 50% of it goes to production. This is very typical. It's not exactly what your plant does. I've seen worse, I've seen better, but this is perfectly representative of a classic plant. 50%. We already know how inefficient air is. 7.5 times the cost to operate a motor with compressed air versus direct electric. Then you're going to go off and you're going to waste 30% of it to leaks, non-ideal uses, which are uses that could be better served another way, such as the air motor, and this artificial demand thing. Air pressure's jacked up. This happens all the time. Piping systems are inadequate. There's lots of leaks rushing through the pipe to create pressure drops. They jack up the pressure. Artificial demand is increased in areas that see that high pressure, and it's really just a whole bag of no good. Leaks. How much can leaks cost us? A quarter or a 16-inch leak, $721, and you'll find lots of these kinds of leaks around the plant. It's particularly with regulators. Regulators have a hole in them. That's what makes them work. They get the bleed so the diaphragm can move, and you have these all over the plant, perhaps. Quarter-inch leak. Look at that. $12,000. Then we have a category of leaks that say that I probably can't hear or feel a $100 leak. And then as the leak becomes worse, where I can both feel and hear it, walking by and I can feel the air on my skin, $800. I guarantee that you have some of these leaks in the plant. Okay, not to badmouth or talk down. That's not at all the point. The point is that they're just out there. I mean, if I had a plant, I'd have them. There's nowhere. You can't get away from them, but you got to keep on top of them and fix them. Sources of leaks. Okay, we have Mr. Forklift driving over hoses, worn cylinder packings. Okay, even gaskets between joints. Sawmills are banging around and eventually gaskets leak. Open condensate traps. That's a big one. Let's just walk over and crack open the bottom of that drain or the bottom of that filter so that it drains all the time, blowing valuable compressed air. Okay, we've got a leak issue right here. Duct tape is just the most wonderful thing. I guarantee you the leaks will find its way through the goop and leak out. Not only that, but this could be a safety hazard. If there's an aneurysm in there, eventually this hose could give way and then we'd have a missile. Oops, go back. Somebody had pointed out something. Exactly. That's exactly right. That's that duct tape right there. Thank you. Okay, this one is a poor choice for a hose clamp. Old-fashioned radiator hose clamp. And just like in your car, eventually they dig through the rubber and you have a leak. So use crimped, rounded, ended connectors instead so that you don't create a leak. Okay, here's a big air use. Remember I said that leaks were really about demand too? Well, it's fun to blow things around and clean up with. The trouble with this is not only does it use a lot of compressed air, but when you blow dust from one corner to the next, well, now it's over there. And then you go over there, and well, now it's back where it was in the beginning. You never really get rid of it unless you use a broom and put it where you want it. So if you've got time to lean, you have time to clean. That's a sawmill guy there working. I was told that when I worked in a plywood mill too. If you're not doing anything, clean up. So please remember, out of all this, we're wrapping this up here. 3 big things. If you're going to, well, you will have at least one part-loaded compressor. Consider variable frequency drive. Consider operating your plant pressure as low as possible, fixing problematic areas where the air can't get to where it needs to go, increase pipe size if you need to, save energy. Lastly, if you don't remove the compressed air from the system, you won't have to replenish it. So fix your leaks. Okay? 3 big things. Next steps. Go find your compressors. I know you have them because you're attending this class. So go lift up the blankets, look under the doors, crawl up in the attics, find your compressors, try to determine what control type you might have and what the pressure settings are. See if there's a possible opportunity for improvement, and then you could talk to PGE, get the Energy Trust involved, and have a project perhaps. So now that you're sort of excited. And then you're going to find out more things too on November 11th or November 15th if you attend that class. I'll give you some more ideas, including Eric's top 10 operation maintenance opportunities. I'm not going to tell you to them now because then you won't come to the class. So come and learn those top 10 operation maintenance. There's some good ones there. But you're going to learn more about the compressed air supply side, demand side, and a little more about how to improve your system. We're going to talk about different things. Controls. There's different types of controls. There's all kinds of neat things you can do with your system. Okay. Receive a free energy consultation. Yeah, it's like voting. You know, you don't have to pay to vote. You can get a free energy consultation. I'm going to voting because that's going to be coming up here, right? So you can call Paula if you're commercial, or you can call John if you're industrial, and they can kind of set you up, take a look at your system. And I think that's it. Beth, please. I'm out of breath.
Thanks, Eric. Thank you, Eric. And I want to remind all of you some upcoming webinars that we have. They're on our screen here in front of you right now. The next webinar is November the 8th, Understanding LEDs. Should be a good one. And then we have some upcoming seminars listed below that, and you can find these and more on our website, energyeducationcenter.com. Before we proceed to the question and answer portion of the webinar, I want to remind you that you can still submit questions to me through chat, and I will ask them of Eric. And within a few days, we'll send you a follow-up email with a recording of this session and the PDF of the materials. And I'd like to draw everyone's attention to a poll, which I just opened in your lower right-hand portion of your screen. If you could take a few minutes to fill out the feedback questions, the survey, we would really appreciate it. We definitely use your feedback to improve future webinars. And now for the question and answer portion. Eric, the first question we have is, does distance from compressor to end use, does distance from compressor to end use affect pressure?
Yeah, great question. It does. Pressure drop from beginning to end is dependent on many factors, what you have in the way, such as filters and air dryers and things like that, the diameter of the pipe, and the length of the pipe. It certainly does. So there are charts available that will give a nominal pressure drop per 1,000 feet of pipe. So perhaps a 4-inch pipe at 1,500 CFM might be on the order of 5 psi per 1,000. Therefore, 2,000 would be 10 psi. So it's just further down the road. You know, you're huffing and puffing, you're climbing up those stairs, and they give you another flight of stairs. Yeah, you're going to get more tired. So yes, it does affect. And that's why it's really important to make sure that your pipe diameter is adequately sized, and maybe you can feed it from the other end. Run another line parallel to it. Connect them down at the end. Good question.
Thanks, Eric. Next question is, most of my clients' plant only requires 80 psi, but they have one piece of equipment which requires 110. Therefore, the whole plant operates at 110. And is there something else I can do for them?
Oh yeah, there's always one bad apple in the group. You've got this pesky little kid that's screaming and yelling, "Give me 110." And maybe you can quiet him down. You can do a couple things. One, you can separate the end use, pull it out, and support it by a separate compressor altogether. And then maybe you have a check valve that would allow the low system to feed in that high system if it dropped down below adequate pressure. But you could separate that out, is my point, and operate the rest of the system at 80. Another thing you might be able to do if it's a relatively low flow use, like a piston that just needs really to keep pressure onto something, clamping force, something like that, but not much flow, you can purchase what's called a pressure amplifier. And they're sort of magical devices that take low pressure and make high pressure out of them without you plugging it into the wall. More on that on November 15th, but that's a really good alternative as a pressure amplifier. Good question.
Great, thanks, Eric. Let's see, we have one more question here. Regarding variable speed control. I have a client with a fairly new compressor which does not have variable frequency drive on it. Can I install a drive on my compressor?
Never fear, proud user of compressed air. I have an answer for you. First off, don't throw your brand new compressor away and buy a brand new compressor, okay? You just bought it. It's a great machine. A lot of compressors, in fact, most of them, can be retrofitted with a variable frequency drive at the cost of about $100 per horsepower. The price of drives have come down dramatically, and I would first of all recommend and insist that you discuss this with the manufacturer, the person you bought the compressor from, and explain your intentions. But in general, rotary screw compressors can be slowed down to about 50% of their speed. So if you have a direct drive 1800 RPM motor, you can slow that down to about 900 RPMs. I just realized I sort of misstated that. What I mean to say is that compressors can be slowed down to about 900. So if you have an 1800, you can slow it down halfway. If you have a 3600 RPM motor, you might be able to slow that down to 75%. But typically you can't go below the 900 mark. But you have to run this by your compressed air distributor first. Good question.
Okay, Eric, we have one more question, and I believe that's all. People can, of course, still submit them to me, but this is the last question I have right now. Our plant manufactures parts which requires cooling. Liquid cooling is not acceptable to us, so we employ compressed air, which blows through 1/4-inch copper tubing with crimped ends. Is there a better alternative?
Keeping things cool in today's environment. Yes, we want to keep our cool. We must keep our cool. Saw blades where we've attached carbide tips on the saw blade, you want to cool them down, but maybe you don't want to damage the metal properties by sprinkling water or oil on them, so we use compressed air. The problem with crimped copper ends is not only are you using expensive compressed air to do the job, but the air that comes out of the crimped end doesn't necessarily go where you want it to go. There's all kinds of fancy words I could throw at it, but I'll just suffice to say there's a significant loss in energy as it goes across that nozzle, and not all of it goes to the part you're trying to cool. Cooling things really, just like when you're outside and you're out working, cleaning your gutters like I was the other day, I'm hoping for a cool breeze. I really just need a breeze by me. So with parts, you can really just create a breeze. Buy a low pressure blower. You just have to move the air across of it. That's all you have to do. No need to expend expensive compressed air to do that job. So consider that. Good question.
Thanks, Eric. That was our last question. I want to thank all of you for joining us today. Please take the time to fill out that feedback survey. Again, we really appreciate that. And we'll stay online for a while in case any of you would like to ask any additional questions. But otherwise, we'll see you again at a future webinar. Thank you.
Thank you.